Um, First and foremost, hello everyone. I would like to thank you for the opportunity to give this presentation. My name is Francisco Baeta. I'm a PhD student from the University of Coimbra, and I will be presenting our work about the development of TensorGP, which is a genetic programming engine in TensorFlow. Uh, just to make sure you can see the transitions in the slides, right? Okay.
Yes, perfectly.
Okay, okay. Just to confirm, sorry. So to start off, as we know, genetic programming is a powerful tool with applications to several problems, ranging from symbolic regression to classification, evolutionary art, etc. One of the main advantages that is commonly attributed to genetic programming is that it represents an automatic problem-solving method, since it does not require any prior knowledge about the problem structure itself. However, the fact that we need to execute every individual of the population for every domain evaluation point and every generation of the evolutionary process makes it so that genetic programming algorithms often require large amounts of computational power. Luckily, and despite this need for computational resources, genetic programming also demonstrates great potential for parallelization, which is the main focus of our work. There are two main methods commonly used to accelerate the evolutionary process in genetic programming. The first being the caching of intermediate evaluation results, and also the vectorization of the domain evaluation. The goal of the first method is to save the results from the execution of parts of code from an individual to avoid re-executing that same code, not only when evaluating other programs, but also in the following generations. This method is useful because the evolutionary process promotes the transmission of highly fit code, and as we know, more often than not, different variations of this same highly fit code appear several times across generations. In turn, the second method aims to abstract the process of domain vectorization by performing one single vectorized operation. This abstraction layer can be useful because on the one hand, it ignores the overhead that is caused by iterating through the set of fitness cases. And on the other, it takes advantage of the parallelization capabilities of modern hardware, be it CPUs or GPUs. There are several numerical computational frameworks that enable data vectorization, as well as operator composition, such as TensorFlow, MATLAB, NumPy for Python, for example, etc. However, for genetic programming in particular, we chose TensorFlow for two main reasons. One being that besides supporting data vectorization, TensorFlow also provides several graph abstractions that can be applied to the caching of intermediate results in genetic programming. The second reason being that one of TensorFlow design goals is precisely to make the distribution of computational effort seamless, which avoids the need for several hardware-specific implementations on our side. For these reasons, in this work, we developed a genetic programming framework named TensorGP to accelerate the process of domain evaluation phase using TensorFlow. Besides, this work also intends on validating the framework by extracting and comparing performance results across different approaches. Most genetic programming systems that are commonly described in literature often use the same evolutionary pipeline, where in a first step we initialize the population, typically using a stochastic method, and then we begin the evolutionary loop by first evaluating the domain of fitness cases for each individual, or in this case for each expression. Then we calculate the fitness of each individual according to the domain values, and then we apply a specific tournament selection method in order to generate the population of the next generation. Finally, if the evolutionary process is not over, we apply the genetic operators, crossover and mutation. After that, we repeat the last four steps until a given stop criteria is met, which is typically the number of generations or the error margin in relation to the target. TensorGP follows this very same approach, which the only difference being the evaluation of a fitness case domain, which is in TensorGP vectorized using tensor operations. Concerning this domain evaluation phase, precisely, we now show the steps for genotype to phenotype translation in TensorGP. We can see that the process to execute an individual in our engine consists of three main steps. The first being the transformation of the initial expression representation, that is a string, to a tree graph, which is only done in the beginning of the evolutionary run. TensorFlow then transforms our tree representation into a directed acyclic graph, which effectively has the objective of avoiding the re-evaluation of identical pieces of code. Finally, we execute the tensor operations that were defined in the TensorFlow graph in order to generate the phenotype, which is a tensor. In the slide, this tensor is represented as an image, as you can see. It is also important to note that TensorFlow has two different execution modes that are called eager and graph execution. And unlike graph execution, the eager model allows for the immediate execution of the tensor operations, but without explicitly building the directed acyclic graph, the step 2 of the translation pipeline that is shown in the slide. Because the individuals we are evolving are constantly changing from generation to generation, we hypothesize that eager execution would instead be a good fit for tensor evaluation. TensorGP also provides a wide range of operators that are meant to ease the evolution towards more complex solutions and also achieve sufficiency through redundancy of operators. Generally, TensorGP operators can be divided into 4 different categories. We have the mathematical operators, the addition, subtraction, etc. Basically the simple arithmetic operators. We also have the logic operators, the conditional operator that is used to conditionally merge two tensors. And then finally, we have the image specific operators such as the warp, the linear interpolation, smooth steps, etc. In the figure of the slide is an example of the use of the warp to distort an image. In TensorGP, more intricate operators like the warp shown in the figure are implemented through a combination of pre-existing TensorFlow primitives. Our implementation of genetic operators follows the traditional approach that was based on the techniques described by Ricardo Poli et al. In the field Quite 2 genetic programming. And as you can see in the set of images to the left, the implemented variant of the subtree crossover produces individuals, images in this case, which features can do in fact resemble the ones from their parents, the two images in the row above. Also in the set of images to the right, we have represented the 4 types of notation operators implemented in TensorGP, namely the subtree and point notation with preserved tree depth. And then we also have the promotion and the motion notation to allow for the exploration of shallower and deeper trees respectively. TensorGP also provides a set of features that are meant to ease the development of genetic programming solutions, including data logging, meaning that before an experiment is executed, a file is created with information for each generation during the evolutionary process. We also have data visualization, meaning that when an experiment finishes, a graph is automatically generated with the evolution of the fitness and depth values. And even though this is done automatically, the user may so choose to disable this option in the initial engine parameterization. Besides, TensorGP also has an engine state that saves information regarding the last evaluated generation in the case the experiment is interrupted for some reason. There is also a way for the user to choose if the initial population is to be generated either randomly or read from another source, for instance, a text file. Besides, currently there are two stop criteria implemented in the engine. One being the traditional, the generational limit, which the engine defaults to, and the error threshold method. Lastly, the engine also enables the definition of customized operators as long as they are declared in the function set beforehand. TensorGP, besides being designed with evaluation speed in mind, one of our main goals was also to make it be a tool ready to be used out of the box. And as it is exemplified in the slide, all we need to do to run an evolutionary experiment is to, in a first instance, write a fitness function. Then we instantiate the engine with the corresponding constructor while passing the relevant parameters. And finally, we call the run method to initiate the evolutionary process. So this example demonstrates that TensorGP is an easy of use framework, as it is possible to prototype and run a full-fledged genetic programming experiment with data vectorization. Now, moving on to the experimentation section, in order to validate TensorGP performance, we ran a series of preliminary tests that were meant to compare different serial, iterative, and vectorized approaches. These initial experiments concern the approximation of the Page polynomial function that is shown in the slide. And we chose this function because it is widely regarded by the community as being a difficult symbolic regression problem to approximate. Because our aim is to compare different approaches, we use a fixed set of a fixed population of 50 individuals, and we did that for every run for all the experimentation. It's also worth noting that each individual was generated using the classic rump half and half method with a constant f of 12. To determine speedups at different domain sizes, we also define a square domain within a constant range and 6 test cases of increasing resolution. The way we did is that each test case has 4 times the amount of evaluation points than the previous test case. The first experimentation consisted of simply raw expression evaluation, and in here we isolated the tensor evaluation phase and considered 6 approaches. 4 of these approaches consist of TensorGP variants that aim to combine the use of GPU and CPU with the 2 main TensorFlow execution modes, graph and eager execution. The 2 remaining approaches, the eval and deep, are simply meant as iterative baselines. Eval is the equivalent of TensorGP, but without the TensorFlow part to provide vectorization. Besides, we also choose to include deep as it is arguably one of the most used frameworks for the prototyping of genetic programming solutions by the community. From the figure, we can see the average execution times for the evaluation of the initial population across different and increasing domain sizes. From the graph, we can verify that TensorFlow using eager execution is faster than graph execution for all test cases, which confirm our initial hypothesis. Besides, eager execution running in GPU is almost 8 times faster than the CPU for the evaluation of a domain with over 4 million data points. We can also see that iterative approaches, deep and eval, exhibit linear behavior, and that TensorGP running in GPU is about 100 times faster than the deep framework. Next, we extended upon this first experiment by including the evolutionary process, and this was done with the intent of testing a more typical genetic programming scenario. For this evolutionary run, we then considered the iterative approaches, along with the ones running TensorFlow in eager mode. This was done because graph execution proved to be systematically slower in the previous experiment. In the figure, Again, we show the average execution times for 50 generations of the same initial population. And regarding this graph, we conclude that regarding TensorFlow, the GPU is about 21 times faster than the CPU for the evaluation of the last test case, which was the one that consisted of over 4 million test points, data points. Furthermore, deep and eval, the iterative approaches follow an approximately linear behavior with an increase in domain size. We can also verify that TensorGP running in GPU is almost 600 times faster than eval for the fourth test case. This increase in performance when compared to the first experiment can be explained not only by the data vectorization, but mostly by the caching of highly fit code that appears during the evolutionary process. So to conclude, we found that using a data vectorization approach, performance gains of up to 2 orders of magnitude are possible using TensorGP when compared to other iterative approaches. We also demonstrated that the evolutionary process benefits from the caching of intermediate results that is made possible by TensorFlow. Lastly, we verified that large evaluation domains take advantage of the parallel architectures, such as the GPU, while smaller problem domains still make the case for the use of the CPU. Now, concerning future work, we intend on expanding upon the preliminary test that was done in this work in order to compare different genetic programming frameworks and approaches within a commensurable evolutionary scenario. And in fact, this is not so much future work as it is partially done already. And we intend on presenting this work in a future venue this year. We also plan to optimize TensorGP by adding an expression preprocessing phase. And the aim of this is to reduce the complexity of the expressions before they are evaluated with TensorFlow. Also, we are looking into incorporating more robust data vectorization solutions, which in our case can be done either by incorporating some TensorFlows with TensorFlow, some operators within the TensorFlow framework itself, possibly in a future version of the framework, or even resorting to other vectorization libraries. So before finishing my presentation, I would also like to take the opportunity to say that TensorGP is publicly available at GitHub, along with a comprehensive documentation of the framework that by now might need some update, but I will make my best to keep it updated. You can also find more about TensorGP by reading our post in the site of Computational Design and Visualization Lab of CISUC, where we actually applied TensorGP to an evolutionary art context. Finally, if you are looking into incorporating TensorGP in your research and for some reason come across some kind of technical difficulty, then feel free to contact me using my email, and I'll make sure I try at least to respond as fast as possible. And in this way, I finish my presentation. Thank you for your time.
Thank you very much, Francisco. You can make your questions either just connect your microphone or say it aloud or in the, the chat.
I actually saw.
I have seen that there is a question by Bill London. I don't know if you can see it. Francisco says it would be nice to have graph using GP operation per second rather than just execution time.
Yes.
Can you react to that? It's not really a question, but...
Yes, sorry for interrupting. Yes, I was reading that, and it's actually very good feedback. We actually have that in the first version of the framework, but when it concerns to these preliminary testing, we actually haven't done the GP operations per second. But thank you for the big feedback. I think it's a great advice, and should complement this presentation very well. Thank you for the feedback.
Thank you very much, Francisco. Any other question? I think we have time for maybe one.
Hi, I have a question. So
please go ahead.
First of all, thank you for the very interesting presentation. And then I wanted to ask you, I use normally GP for control purposes, so to find the control laws. And I wanted to ask you, do you think that TensorGP would be helpful in this process? And by that, I mean that to find the fitness function of the individual, I have to propagate the equation of the dynamics for the system, and that it's a very time-consuming process. So do you think that TensorGP could help in that?
The TensorGP could help in that regard, mainly if the domain evaluation is very extensive. So, okay, maybe if I go a little bit before, we can see that TensorFlow really shines for the evaluation of large problem domains. So I'm not familiarized with that specific, with your specific application scenario, but if you have a very large evaluation domain, if your target has a lot of data points, then it might benefit from the vectorization of the operation using TensorFlow, and specifically using parallel architectures such as GPU. Now, with the rise of GPU computing in the last decade, they have become very commercially available, and I don't know, at least I think the speedups that you can get in this regard are really mind-blowing, I would say.
Okay, thank you. So it's worth trying. Thank you.
We also have...
Thank you. Yeah, I don't think we have the time because it's 9:54 and the next one is scheduled to 19:55. So just, I mean, thank you very much, but maybe you can answer the question in private. So let's just, I mean, say virtual applause for Francisco. And thank him for this interesting presentation, and also for releasing his software as free software. I think that everyone should do that.
Thank you.
And